Hello students. In today's warm-up, or in today's class, we're going to be working on continuity. So let's get started on these two quick warm-up problems. So in this particular set of problems, they want us to find the limit as x approaches infinity. Now remember, for all of these, we're going to want to use our arithmetic for functions to split them up. So this should be 1 divided by 2x squared minus cosine squared x divided by 2x squared. You'll notice that the limit as x approaches infinity for this particular equation, because it is a fraction, even though I didn't write the fraction bar until just now, as x approaches infinity, this one will get larger and larger and larger. So 1 divided by 2 times infinity squared will eventually converge to 0. Then we have our minus sign. And then, as you'll remember, cosine squared of 0, or cosine of 0, is 1. 1 divided by 2x squared, which, again, because you're dividing by 2x squared, and x squared will approach infinity, this will eventually become infinity. So the limit as x approaches infinity is 0. For example 2, we want to split this up again. So this will be x times sine of 1 divided by x. The limit as x approaches infinity here will be infinity times sine of, well, let's pretend that infinity approaches 10,000. You'll remember that sine of 1 divided by 1,000, and as this approaches infinity, we'll get closer to 0. So we're really looking at sine of 0. Sine of 0 is obviously 0. So infinity times 0 is 0. So that is our limit for those two problems. So in this video, we are going to be working on continuity. So you already know what continuous is. Continuous means goes on forever and ever or doesn't have any breaks. So the definition is the graph of a function is continuous if you can draw the graph without lifting your pencil off of the paper. So that's how we see it visually. A function can be continuous at a point even if the whole graph is not continuous. So then we can start looking at continuity in terms of intervals or areas. So we are not going to look at figure 219 because we're going to do it on this video. Now a function y equals f of x is continuous at an interior point c of its domain if the limit as x approaches c for the function is equal to f of c. So what this particular statement is saying is that the limit as x approaches some number for a function is continuous if I can substitute that number in and it's the same exact limit. So we'll do that on the next problem. The next bullet says a function y equals f of x is continuous at a left endpoint a if the limit as x approaches a from the positive side of f of x is equal to f of a. The last one says a function y equals f of x is continuous at a right endpoint b if the limit as x approaches b from the negative side of f of x is equal to f of b. So I know I just gave you a lot of words there, but we are going to show you that in the next slide. Not this one, but the next. So let's talk about discontinuity a little bit more. Now first we know what continuous is. It's any function that can be drawn without lifting your pencil. So consider anything that will not have a break in there. A removable discontinuity means that we have a hole. So if you can fill in the hole, then the discontinuity is removed. A removable discontinuity we just talked about, that's anything with a hole. Jump discontinuity is if there is a break in the graph. So imagine a step function. Infinite discontinuity is easiest seen by the graph y equals 1 divided by x. And then we have oscillating discontinuity, which means that the function is going to oscillate so much that it's very difficult to determine its continuity. So let's look at that a little bit further. So a removable discontinuity is something like this. So you'll notice that there is a limit. Both sides approach the same number, but once they get to this limit over here, there is a hole. So that's a removable discontinuity because technically we could fill that hole and it's no longer discontinuous. This one right here, as you would have guessed, is a jump discontinuity because from here to here, the graph jumps from this lower portion to this upper portion, hence the jump discontinuity. This graph right here is called an infinite discontinuity because both sides, or a side, approaches infinity. Just like the limit as x approaches 0 from the negative side is negative infinity. This graph right here is an oscillating discontinuous function because if you pick a point, let's say 0.001, and you pick a point right next to it, 0.002, the graph would have fluctuated so much that it's really difficult to determine where actually the limit exists. So, again, a continuous function, or a function is continuous on an interval if and only if it is continuous at every point in the interval. A continuous function is continuous at every point in its domain. So notice the difference there. You can have continuity on an interval, and you can have continuity on an entire function. So these two pieces are key. We're going to look at these in the several examples to follow. It says that all algebraic combinations, plus, minus, multiply, and divide, of continuous functions are continuous where they are defined, where they're not dividing by 0. And the composition of continuous functions are also continuous. For example, sine of x squared. So let's take a look at, actually, let's go back really quick and talk about continuous functions at a left endpoint and at a right endpoint. Going back to these graphs of functions, or of limits, looking at this particular function. As the graph approaches 0 from the positive side, we'll see that it's continuous there because it actually has a value. And we'll see here that these two are not going to be continuous because their endpoints are not the same there. So it's kind of like looking at the limits. Now, let's go back to this particular problem here. Now notice it says, do not use your calculator. Determine if the function is continuous. Support your answer. So, without using the calculator, we always want to solve for the denominator to find some asymptotes. Now, if you look at the following denominator, we have x plus 2 equals 0. And if we solve for x, we find that this graph exists everywhere except when the graph is equal to -2, because then you're going to have an undefined function. So at this graph, we could say that the domain is all real numbers where x is not equal to -2. So this is our domain. And also our point of discontinuity is at x equals -2. So notice all we did there is we solved the denominator for x. So let's move on. So here it says find the points of discontinuity for the following function. Identify each type of discontinuity. So let's first start by graphing these, or by factoring these. Now, the numerator is a little complicated, so feel free to, at this point, graph it on your calculator and find your zeros there. Because I wrote this problem, I should already know these, and I know that it's at x plus 2, x minus 1, and x plus 1 and x minus 3. And the denominator is the difference of 2 squared, so that's x minus 3, x plus 3. So here's the key point to notice. We have an x minus 3 on the numerator, and we have an x minus 3 on the denominator, so we can cancel those out. We would be left with x plus 2, x plus 1, all divided by x plus 3. Now we know a couple things. We know 1, at x equals 3, that's when we originally had x minus 3 on the denominator equals 0. When we solve it, we get x equals 3. This is a point of discontinuity. And this point of discontinuity is a removable point of discontinuity. Because we were able to cancel it out, it tells us that there's just merely a hole in the graph. Now, what's left in our function is this x plus 3. Now, if we solve x plus 3 equal to 0, we get x equals negative 3. This gives us a vertical asymptote. And because we have a vertical asymptote, this discontinuity is an infinite discontinuity. So again, vertical asymptotes automatically equal an infinite discontinuity. Values that were canceled out give us a removable point of discontinuity. So in example 2, they want us to give the expanded function that is continuous at the indicated point. So here's how this works. We would take the same exact function that we had and begin to factor. So this will be x plus 2, x plus 1, times quantity x minus 3, all divided by x plus 3, x minus 3. Now again, we can cancel these out, the x minus 3's, and we're left with the function x plus 2 times x plus 1, all divided by x plus 3. And this is what our expanded function would look like. The only other thing I would do to clean this up is I would redistribute. So that gives us x squared plus 3x plus 1, all divided by x plus 3. And that would be our expanded function. So again, all we did to find the expanded is we factored, simplified, and that's what our expanded function looks like. So the next thing I want to mention is the intermediate value theorem. So the intermediate value theorem states that if f of x is continuous on a closed interval a, b, then the function f of x takes on every value between f of a and f of b. So what that means is if we go back to our equation, so let's look at y equals 1 divided by the quantity x plus 2. And so let's graph this really quick, just so you have a better idea. So y equals 1 divided by square root x plus 2. So you'll see the following graph here. Now, as you can see, when we get to negative 2, this graph doesn't exist. It means we have a infinite discontinuity because we have a vertical asymptote at negative 2. So what we can actually say based on this intermediate value theorem is that we have a continuous function here from the interval. Let's write this out. The function is continuous when x is greater than negative 2. Or we could just say from the interval negative 2 to infinity. And notice that I did not include the negative 2 because there's an asymptote there. So from negative 2 forward, it's continuous. So if we wanted to use the intermediate value theorem because it says closed intervals, we could say from negative 1 to infinity, the function is continuous. And again, because we gave this closed interval, a to b, it says that any value I pick from f of negative 1 through f of infinity would exist. That means every value for the function from negative 1 to infinity exists, and it's continuous. So that's how we use the intermediate value theorem. There's going to be other uses, but we won't dig into that just yet. Now, we're going to be working on this the majority of the week, so as you have questions, please let us know. We're going to do one more example problem. It's very similar to what we've done in the past. So determine if the function is continuous, which we can show. So support your answer using a composition of functions. So this way we can make this a little bit more tangible for you. So we are going to say that this is a composition of functions from f to, let's get some math in here. Let's pretend this is our little composition sign, f of g. And we are now going to define f and g. We're going to say f of x is equal to 1 divided by the square root of x. Or say g of x is equal to x plus 2. Now we have two functions here, and we could say that g of x is inside of f of x, and now we're going to prove that each one of these is continuous. So we know that 1 divided by the square root of x, we know that that's continuous. We know that it's continuous when x is greater than or equal to 0. And we know that g of x, we know that g of x is continuous for all real numbers. So together we could say that f of g is continuous when x is greater than or equal to 0. Oh, my mistake. We know that both of these functions are continuous. Let me restate that. We know both of these functions are continuous where I said they were. But when we put the functions together, we know the function f by g of x is continuous when x is greater than or equal to, or when it's greater than negative 2. Otherwise, we'd have that undefined on the denominator. So together, they're continuous when x is greater than negative 2. So, please make sure you're ready to ask questions in class. That's all for now. I'll see you guys next time.